Hello. Today we are moving to section 11.5. Section 11.5 is application analysis of algorithm efficiency 2. As you remember in section 11.3, in section 11. Give me a second. In section 11.3, we learn the same topic, but this was just one in that topic, in that section, that was application analysis of algorithm efficiency 1 that we learn in section 11.3. Now it is section 11.5 where we learn the second part of that section. All right, the second part of that section. All right, so this is a long section, so I'm going to split this section into parts. So the first part of the section, today we have the first part of the section. All right, at the beginning we have some theory parts. Let's read this. I will read this and then explain to you. Have you ever played the guess my number game? This is a fun game you might have played when you were a little kid. This is how this game goes. A person thinks of a number between two other numbers, say number 1 and number 10, or maybe number 1 and number 100, for example, and you try to figure out what it is. Right? So one person guess a number, so other person have to find the number the other person already chosen. Okay, using the least possible number of guesses. All right, so every time you make a guess, and your opponent will say whether that is the number he thought, or the number he thought is less than the number you told to that person, or greater than the number. Okay, depending on the response, you can just guess the next number. All right, so you have to keep on guessing until you find the number. So the person who gets the minimum number of guesses will win the competition or the game. All right. All right. That's explained in this section. Let me read the last sentence. Each time you guess a number, the person tells you whether you are correct, too low or too high. All right. If you have played this game, you have probably already hit upon the most efficient strategy. And there's a strategy for this game. You might not know when you were a little kid. There's a most efficient strategy that is actually begin by guessing a number as close to the middle of the two given numbers as possible. All right, so you have to guess the middle number. All right, so this is the best approach, the efficient strategy of this game. As an example, if the numbers are between 1 and 10, so you have to guess the middle number. Maybe first you have to guess 5. Okay, if the person says less, then you have to guess a number between 1 and 4. All right, let's say that is 2. And then if the person says greater, then you have to guess a number. The number, of course, if that person says greater, the number is 3. If the person says number is less, then the number is 1. Okay, so this is the efficient strategy to reach to the number. All right. If your guess is too high, then the number is between the lower of the two given numbers and the one you first choose. If your guess is too low, then the number is between the numbers you first choose and the higher of the two given numbers, like I explained to you. right? So it is an easy game. It's those kind of problems are known as divide and conquer. Okay, so always you divide the possible interval into two halves. Here the numbers are from 1 to 10. First you could guess 5. If the person is, say, let's say bigger, then you have to guess number between 6 and 10. Okay, so you can always guess the middle number, which is maybe 8, and so on. All right, so let's move to the next slide. In either case, you take your next guess. You take as your next guess a number as close as possible to the middle of the new range in which you know the number lies. You repeat this process as many times as necessary until you have found the person's number. All right. The technique described previously is an example of a general strategy called divide and conquer. So these kind of approaches are called divide and conquer, which works as follows. To solve a problem, reduce it to a fixed number of small problems. Okay, you reduce it to a fixed number of small problems of the same kind, which can themselves be reduced to the same fixed number of small problems. You are still dividing into smaller and smaller problems of the same kind, and so forth until easily resolve the problem you obtain. Okay, that's called divide and conquer. You divide until you get a very small problem, so you then solve these small problems. That will give you the answer for the bigger problem. That is called the divide and conquer. In this case, the problem of finding a particular number in a given range of numbers is reduced at each stage to find a particular number in a range of numbers approximately half as long. All right, so you understand that. Always you just work on half of the initial length of the possibilities, because you know whether the number is greater than or smaller than to the number that you already guessed. All right, now let me read this. It turns out that algorithms using divide and conquer strategy are generally quite efficient. Okay, they are quite efficient. Divide and conquer approaches are quite efficient. Nearly always have orders involving logarithmic functions. The order involving logarithmic function. That's good, right? People like the logarithmic functions. Okay. People like to have logarithmic functions or orders. All right. In this section, we define binary search algorithms. We are going to define binary search algorithm, which is the formalization of the guess my number game described previously. And we compare the efficiency of binary search to the sequential search. You have already learned sequential search in one of the previous section. So you compare binary search to the sequential search. Then we develop divide and conquer algorithm for sorting. Now we move to sorting. Previously it was searching algorithms. Now we are going for sorting algorithms. All right. Under searching algorithms, we learn merge sort and then compare efficiency of the merge sort to the insertion sort and then the selection sort. All right. So you have already learned insertion sort, and now in this class we are going to learn merge sort and selection sort. Okay, we are going to learn merge sort and selection sort. This is we have already learned the insertion sort. All right, so that is the summary of that's the structure of this section. Let's move to the next slide. Whereas sequential search can be performed on an array whose elements are in order, so which is important. Elements should be in order. All right. A binary search can be performed only on an array whose elements are arranged. Okay, so in this case, the elements should be arranged. They are in some kind of order. All right, let me mark it here. If you want to apply the binary search, the element should be arranged. Okay, element should be arranged. Otherwise, you can't perform the binary search. Okay, if you are given unarranged a list of elements, then the first step is to arrange the list into the ascending order or to the descending order. All right, and then apply the binary search. Okay, then apply the binary search. All right. Then you have this array, given an array a1, a2, dot an of distinct elements arranged in ascending order. So they are arranged already, they are in the ascending order. Consider the problem of trying to find a particular element x in the array. Now you are given this array, you have to find the element x in this array. And to use binary search, first compare x to the middle element. So you compare this x to the middle element, like the game that we discussed. Can you remember the game? We discussed a game. Let me go back. Guess my number game. It is like the guess my number game. All right. You have to compare x to the middle element of the array. If the two are equal, then the search is successful. All right. If x is equal to the middle element, then search is successful. If the two are not equal, then because the array elements are in ascending order, they are already in ascending order, compare the value x and the middle array element. Middle array element narrows the search either to the lower sub array, that means consisting of all the array elements below the middle element, or the upper sub array consisting of all the array elements above the middle element. This is actually this is same as the guess my number game. Okay, let's say you have these numbers. Let's say you have these numbers like number 1, 2, 3, 4, 5, 6, 7, 8. Now it's 1, 2, 3, 4, 5, 6, 7, 8. Now you just add 1 to 8, which is 9. So divide 9 by 2, which is 4.5. So you can get the least element, the integer less than 4.5, which is right here. All right, now you compare the number you want. Let's say you are searching for 3. So let's say x is 3. Then you compare x with 4. Since 3 is less than 4, now you just keep your eye on the array less than 4, which is which consists numbers 1, 2, and 3. All right. So that's the first iteration. So this is the lower half, and then that is the upper half. Okay, let me mark them. This is the lower subarray. This is the upper subarray. This is upper. All right. So you have lower subarray and upper subarray. If x does not equal to 4, then you just check the lower subarray or the upper subarray, depending on whether x is greater than 4 or not. All right. So that is explained here. The search continues by repeating this basic process over and over on successively small subarrays. Okay, it terminates either when a match occurs or when the subarray to which the search has been narrowed contains no element. All right, so there are two possibilities. Either you meet the corresponding value or the element in the previous example. So what will happen is you have to go to the lower subarray. So the lower subarray will look like this. Let me write this thing. X is smaller than 4. That means lower subarray. All right. Then you consider this part which has 1, 1, 2, 3. So this is that. All right. And then you just add 1 to 3 and divide by 2, which is just 2. So this will be your middle element. That's the middle element. And then your x is still 3. Now you check x to this number. You compare x with 2. You see x is greater than 2 now. That means you have to get the upper subarray. All right, so let me mark the upper subarray here. Let me delete this color. That means I will mark this. This is the upper subarray and that is the lower subarray in other case. I will use the same colors like before. Orange for the lower, blue for the upper. Okay. And then you have only one element, that is x equals 3. Only one element left, which is 3. All right, that is the corresponding number is 3. That is x equals 3. All right. Let me mark this in blue. All right, so this is the algorithm I explain in this slide. Okay, that's what I'm explaining right here. All right, so let's go to the next slide. The efficiency of the algorithm is a result of the fact that at each step, the length of the subarray to be searched is roughly half the length of the array of the previous step. All right. To compute the efficiency of the algorithm, you have to understand this argument. The argument is the length of the subarray to be searched is roughly half of the length of the array in the previous step. All right. This process is illustrated in figure 11.5.1. All right. So this is figure 11.5.1. As I explained you before, you have the left sub array, and then you have the right sub array, and then you have the middle element. All right, so you compare x with the middle element. If x is less than the middle element, you just search on the left sub array. If x is greater than the middle value, then you search on the right sub array. All right. Here we say right and left subarrays, but there we call them lower subarray and upper subarray. Please understand both are same. It doesn't matter you say lower subarray or upper subarray, or um, left subarray or right subarray. They all are same. Left subarray, right subarray. Okay, they all are same. Then this is the algorithm. Algorithm 11.5.1 binary search. I explained this algorithm in the previous slides, so I'm not planning to explain it now. I will give a quick summary on that. In this algorithm, first you have to initiate the variables. First, you can initialize index to be 0 and bot means the bottom equals 1, top equals n. All right, then what you do is you just compute this middle element, which is bottom plus top divided by 2, and the floor function. You can remember this is the floor function. All right, this is the floor function. Floor function of bottom plus top divided by 2. All right, and then you compute the mid index like that. Thereafter, if mid equals x, then index equals mid. So that is the end of the algorithm. The algorithm stops right there. If a mid greater than x, then you just initialize or the assign top equals mid minus 1, bot equals mid plus 1. All right, and then you run the while loop until these two conditions are met. The conditions are either index to be non-negative. Okay, if the index is 0, the while loop runs. In order for while loop to stop, index should be non-zero, and as long as top is greater than or equal to bottom, the algorithm runs. Okay, so let me explain these two cases. This is the case where the element is found Okay, so this is the case where element is found. This is the case where element does not exist. The element does not exist. Depending on these two stopping criteria, you can understand whether the array has the required element or it found the element. If it found the element, it stops. If the array doesn't have the element, it again stops. Give me a second. All right, so go forward. So here we have an example. Trace the action of algorithm 11.5.1 on the variable index, bottom, top, mid. So these are the variables you have to trace: index, bottom, top, mid, and the value of x given in part A and part B below for the input array of, this is the input array. All right, so there are 10 people. The first one is Anne, the next one is Dawn, Eric, Gail, Juan, Matt, Max, Rita, Suji, and Yuan. All right, so these are the 10 names. And then first you have to find Eric in that list, and then you have to find Sarah in the list. You see that Eric is there in the list, but Sarah is not in the list, all right? Sarah is not in the list. So let's see what happen if that element is not in the list. This element is not, okay, so this is not in the list. All right, let's try the algorithm here. I'm running the algorithm. So this is the order, the ascending order of the names. Okay, ascending order of names. Names are starting from A and then D, E, G, J, like that. So that's the ascending order if you just consider the alphabet. All right, then you have to initialize indexes. There are 10 people, so this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So the index should be 0 at the beginning, and the bottom is 1, top is n, which is 10. Okay, so I initialize like that, and then x is the variable, which is Eric here. So go to the first iteration, you go inside, now let me write it here. Mid, let me write it over there. Mid equals 1 plus 10 divided by 2 and the floor function, which is 5.5, the floor function, which is 5. So the mid value is 5, which is right here. And then you have to compare mid value with x. A mid should be, A5 is Juan, all right, which is less than Eric. which is x. Then you have to go to the then you have to go to that case. Okay, since give me a second. Actually, I made a mistake here. So this symbol should be other way around. Eric is less and Juan is big. You know, the reason for that is this is greater than that. Okay, Juan comes later, Eric comes early. So then Juan should be greater. Alright, because of that reason, you have to go to this option. That means this is satisfied, this if loop is satisfied, then you go there, and then your top equals mid minus 1, which is 4. Alright, so I put 4 here, and bottom equals the same bottom like before. Okay, the bottom is same like before, which is 1. Okay, so here it is 1. So let me mark this in a different color, maybe that. So this is right here. All right, so let's go to the next step. And the index is still 0. All right, in the next step, again you compute mid, which is bottom plus top. Bottom is 1, top is 4 divided by 2, and then the floor function of that, which is 2.5, the floor function, which is 2. So this is your new mid value, which is right here. And then you have to check a of 2, which is down. And then you have to compare John with Eric. Actually, Eric is bigger than John. I'm sorry, Eric is bigger the other way around. Which is x. Then you have to go to this condition is not satisfied, so you have to go to the other case. Now bottom equals mid plus 1. All right, now bottom equals mid, which is 2 plus 1, which is 3. All right, so I got bottom to be 3 here. Okay, bottom 3, then 4, top remains constant. Top doesn't change, which is 4. And the index stays 0 still. Okay, so this is the next case, which is marked here. All right, now go to the next case, next step. Let me move this one. All right, now let's discuss the next case. Now mid equals, now our top is 4, bottom is 3. 3 plus 4 divided by 2, the floor function, which is 7, and 3.5, the floor function, which is 3. So the mid is 3, and then you have to compute a of 3, which is Eric, which equals Eric, which is x. Okay, so you found the answer. Okay, that's done. All right, so the corresponding index is 3. This is the corresponding index of the location where Eric is in. Okay, so you put that index right here. Okay, so let me mark this in a different color. So that is right here. All right, so that is searching for Eric, and then we search for Sarah. The next part is you have to search for Sarah. All right. Okay, so this is Sarah. She is not in the list actually. You can see she is not in the list. Anyway, let's see how the algorithm performs in this case. First, we have to initialize the variables, index, bottom, top. They were same like before. All right, then we have to compute the mid. Mid equals 1 plus 10 divided by 2, and the flow function, which is 5.5 flow function, which is 5, and which is right here. And then you have to find A5, which is Juan, and then Sarah, which is x, is greater than Juan. If you consider the alphabetic order. All right, since Sarah is greater, you go to this case. In that case, bottom equals mid plus 1, which is 5 plus 1, 6. So you have that information here. Then top stays as same, which is 10. So this information is right here, which is equal to that, which is equal to this. All right, and then let's move to the next case. And then you take the upper half, again compute mid, which is 6 plus 10 divided by 2, which is 8. All right, which is just 8. That is the mid number, which is right here. And then compute A8, which is Rita. Okay, Rita is greater than, Sarah is greater than Rita, because S comes after R, which is X. So in this case, again you are there, because this is not satisfied. All right, so you are there, then the bottom equals mid plus 1, which is 8 plus 1 equals 9, top equals 10. All right, so it is 9, bottom is 9, the top remains as 10, this is 10, 0, 0. I forgot to put those numbers. All right, so this is the next case. Let me color this in completely. So this is the next case. I will color it with this color. All right, let's move to the other case. Now you have to compute mid again. Which is bottom 9, top 10, 9 plus 10 divided by 2, the floor function, which is 19. This is 19 divided by, that is 9.5, which is 9, which I mark right here. And then A9 should be Suji, which is greater than Sarah, which is X. Okay, now that means this is satisfied again. X is smaller, then top equals mid minus 1. Mid is 9, 9 minus 1 is 8. And the bottom, it remains same. Bottom is 9. Now there's something here. Top is 8, bottom is 9. Let me get some space here. Top is 8, bottom is 9. You see that? So this is impossible, right? The top should be greater than bottom, but here it didn't happen. This is greater. 9 is greater than 8. That means the bottom is greater. Because of that reason, this while loop, this does not satisfied. Okay, so that is violated. Since that is violated, stop. So you just stop the algorithm. That means algorithm is aborted. Or maybe the algorithm met the stopping criteria. I just write a stop. The algorithm met the stopping criteria. The conclusion is Sarah is not in the list. All right. All right, good. So let me mark this in a different color, which is right here. This is still 0. This is 9. Right, so that is end of the example, and then let's move to the next slide. Now talk about the efficiency of the binary search algorithm. First I will read this and then I will explain. At each stage of the binary search process, the length of the new subarray to be searched is approximately half that of the previous one that we know already. And in the worst case, every sub array down to a sub array with a single element must be searched. All right. So in the worst case scenario, okay, in the worst case scenario, you are just dividing this until you have just single element. All right. Until you have the final single element. All right. So that is the worst case scenario. Worst case scenario is subarray with a single element must be searched. Okay, which is the worst case scenario. All right. Good. Consequently, in the worst case, the maximum number of iterations of the algorithm's while loop is one more than the number of times the original input array can be cut approximately in half. So you keep on cutting the original array into halves, and the complexity, which is the number of times the while loop runs, the complexity in this problem, we only consider the while loop. We just consider how many times the while loop runs. So what we do is the maximum number of iterations of the algorithm's while loop runs is one more than the number of times the original input array can be cut approximately into half. That is something like this. Let's say this is the given array to you. 1, 2, 3, 4, 5, 6, 7, 8. So you just keep on cutting into halves, and then every time it goes through an iteration, and then finally what will happen is at the end either this satisfied or that satisfied, so the while loop stops. All right. So you just keep on dividing. So you take this 9, this as the middle element, and then you consider this sub array or that sub array. Okay, then if you consider these two, and then you consider this as the middle element, so this sub array is right there, that sub array is right there. Here you consider this as the middle element, so this sub array is right here, that sub array is right there, and then finally you consider these two as the sub array, and then you take that as the middle element. So finally you have 8. Okay, you keep on doing that until you get the final element. So here you have 1, here you have 3, here you have 5, and then here you have 8. All right, so you keep on doing until you have the single elements in the sub arrays. Okay, here 3 single elements in the sub arrays. I'm sorry, 4 single elements. All right. That means it runs through this many iterations. It is just one iteration number 1. Let me mark them here. 81, iteration number 2, iteration number 3. All right. Now there are 3 iterations. Other than that, finally you have to just run another time through the while loop again. Finally you have to run this again through the while loop. To check, there are two things you could check: whether top is top is greater than or equal to the bottom, and index equals 0. All right, so then this counts just number. This is the thing that we consider as 1 here, just 1, that is right here. This part, let me mark with a different color. This one is that, and these iterations are right here. Number of times the original input array can be approximately cut into half. This part, which is right here. This is that. All right, I assume that everybody can understand that, how it comes. All right, now go to the last paragraph. All right, now if the length n of this array is power of 2, that means n is equals to the power k for some integer k, then n can be halved exactly. K equals log of n to the base 2, which is the floor function of log of n to the base 2 times before an array of length 1 is reached. So this is something easy that I'm going to explain you right here. Let me explain it right here. That means let's consider n equals something like 2 to the power 3. All right, that means 8 elements. So you have 8 elements like before. So we wrote 8 elements before. So let me copy that. So this is the case where we have 8 elements. All right. Here, how many iterations are there? There are 3 iterations. There are 3 iterations. That means there are 3 iterations, which is similar to that number over there. Here 3, there are 3 iterations. All right, now go to the next case. Now just consider something like n equals 2 to the power 2, which is 4, and then it will look like 1, 2, 3, 4, and then you find the middle element, which is 1 plus 4, which is 5 divided by 2 is 2.5, and then get the floor function of that. So then this will split like this. 1 and 3 and 4, and this is 1, and then what do? You just add 3 and 4 and divide by 2, which is 3.4, and 3.5, then this floor function of that one is 3. So these are the singleton elements you get. You get 1 and 4. Okay, let's consider how many iterations are there. So there have been 2 iterations. Okay, there have been 2 iterations. You see this number is 2 and 2 iterations. So they are related actually. Number of iterations related to the number right here. If n is in between 2 to the power 2 and 2 to the power 3, actually it is the floor function. All right. So let me copy this one over there. This part is actually for this information. All right. Now what I say here, now you have to solve this for k. Then that for that you just get the logarithm of n. Logarithms of both sides. From here you can get log of n equals log of 2 to the power k, which is k log to the base take to the base 2. Which is k. That means k equals log that k equals log of n to the base 2. Okay, which is right here. And then you put the floor function of that. If n is in between 2k and 2k plus 1. All right. Now let's go to the next slide. If n is not a power of 2, then n equals 2 to the power k plus m. That's true. N is not necessarily 2 to the power, something like 2 to the power k. Sometimes you have n equals 2 to the power k plus m for some integer k, where this for some integer not k, m. Yes, for some integer k, this m should be smaller than 2 to the power k. Okay, so you can read this and understand how it comes. And thus n can be split approximately in half k times also. And so in this case, k equals that, the floor function that like we learned early right here. Okay, like we learned right here. It is just the flow function, because n can be in between 2k, 2 to the power k and 2 to the power k plus 1. Alright, so that is given right here. So this is the result that we have already discussed in the previous slide. Thus, in the worst case, the maximum number of iterations of the while loop in the binary search algorithm is this. Okay, so this is from the iterations from and this one is from the while loop when while loop runs to check this condition. From the iterations, and this is from the final check of top greater than or equal to the bottom and index equals 0. All right, and then the corresponding O notation of this one is given like that. Okay, let me explain how it comes. You know that log of n to the base 2 flow function is less than or equal to log of n to the base 2 log of n to the base 2. All right, and then you can add 1 for the both sides. Log of 2n the flow function plus 1 log of n to the base 2 plus 1. We know let me write something else. You could just write this as like this too. Log of n to the base 2 plus log of n to the base 2. You can just replace this one by that if you just replace it by a smaller than or equal to symbol. All right, then this is 2 times log of n to the base 2. In the previous section, we learned that 2 log of n to the base 2 is big O notation of log n to the base 2. Okay, thus by 1 you write log of n to the base 2 the flow function plus 1 also or log n to the base 2. All right, so this is the answer, which is right here. Okay, these things we have learned already. We have already learned these things. We learn about big O notation, big omega notation, and big theta notation. All right, so that is the end of the section, end of this part of the section. Let's meet in the next day. Thank you very much.